So, China just turned off the tap. Not metaphorically, actually halted exports of rare earth elements right in the middle of an already chaotic trade war with the United States. And if you've been paying even half attention to the news cycle over the last couple of years, you know that move landed like a brick through a window, because rare earth elements are not some niche industrial curiosity. They're in the magnets inside every electric vehicle motor, every wind turbine generator, every piece of defense hardware that Western militaries have spent decades designing around the assumption that the supply chain would just keep flowing. So that's the backdrop. China squeezes the supply. Washington starts making very unusual territorial noises about Greenland, which, again, is a real thing that actually happened, not a bit. And the United States and Ukraine sign a mineral resources agreement that is, at its most generous reading, not purely about Ukrainian reconstruction. Everyone suddenly is thinking very hard about where their critical minerals come from. And into this moment walks a professor of materials chemistry at Uppsala University in Sweden, with what is, on the surface, a fairly quiet announcement about cataloguing mineral deposits, not opening a mine, not launching a geopolitical minerals alliance, cataloguing, taking inventory. And yet, the more you look at what Martin Sahlberg and his team are actually trying to do, the more the question becomes genuinely interesting. Can Europe mine its way out of strategic dependence on China for rare earths? And more specifically, can Sweden, a country with real deposits, relatively cheap energy, and an apparently sincere interest in leading the green transition, build something that isn't just a map of rocks in the ground, but an actual alternative supply chain? That's what I want to dig into today, because the research is real, the deposits are real, and the geopolitical pressure making all of this suddenly urgent is very, very real. But there's also a gap between a university research program and an operating mine that you could drive a truck through. Several trucks, actually, probably for decades. So let's take it seriously without taking it at face value. Here's what the Uppsala team is actually doing in plain terms. Martin Sahlberg's group is not going out to find new rare earth deposits. Sweden already knows where its deposits are. Kiruna in the north, Bergslagen in the central region, and Norraka outside Gränna in the south. What Sahlberg is doing is something that sounds almost mundanely practical, but is actually a genuine methodological shift in how you think about mining and manufacturing together. Historically, when you mined for a specific metal, iron, copper, gold, whatever, you go in with a target. You pull out the thing you want, and everything else is either waste or a secondary consideration. That's how the industry has operated for a very long time. What Sahlberg's team is proposing is to first take a comprehensive inventory of everything that's actually in these Swedish deposits, every element in whatever proportions nature put them there. And then, and this is the key move, instead of asking, how do we process this ore to match the formulas used in existing magnet manufacturing, they flip the question. They ask, given what's actually in the ground here, what magnet recipes can we design that work with those naturally available elemental combinations? Sahlberg's own description of this is genuinely charming. He compares it to the TV show What's in Your Fridge, the cooking format where the challenge is to make something good from whatever ingredients you actually have, rather than going out to buy exactly what a recipe specifies. You work with what's there. You design around the ingredients rather than forcing the ingredients to conform to the design. It's a small conceptual shift that has potentially significant practical implications. Because if your magnet formula is built around the specific elemental ratios that naturally occur in Swedish ore, you potentially need fewer processing steps to get there, which means less chemical intervention, less waste, and a more economically viable domestic operation. We'll come back to whether that potential is likely to be realized, because there are real complications. But the core idea is sound, and it's not what the rare earth industry has traditionally done. Now, before we go any further, I want to clear up the thing that confuses almost everyone the first time they encounter this topic, because it's baked right into the name. Rare earth elements. They sound like they should be vanishingly scarce, like truffles or working printers. They are not. Geologically, most of the 17 elements classified as rare earths are actually relatively abundant in the Earth's crust. Cerium, for instance, is more common than copper. Even the less abundant ones are not geologically rare in any meaningful sense. The name is a historical artifact, and it has caused a lot of people to have the wrong mental model of what the actual problem is. The problem is not that these elements don't exist in sufficient quantities. The problem is concentration. To make extraction economically viable, you need deposits where rare earth elements occur in high enough concentrations that the cost of getting them out of the ground and separated from everything else makes commercial sense. Most places where rare earths exist, they exist in concentrations too low to bother with at current market prices. That's the real bottleneck, which is why Sahlberg's comment about Sweden's position is worth taking seriously. He says that Sweden's possibilities for extracting rare earth elements, even when compared internationally, are relatively good. That's not boosterism from a guy who just wants funding for his department. The deposits at Kiruna, Bergslagen, and Norra Kärr are genuinely known quantities. Norra Kärr in particular has been studied extensively and is considered one of the more significant rare earth deposits in Europe by grade and composition. These are not trace amounts in random Swedish bedrock. They are deposits that have been assessed as potentially competitive by international standards. So the starting point is legitimately promising. Sweden has real concentrations in known locations. The geological work is not starting from scratch, and there is an institutional research effort now focused on connecting what's in the ground to what could come out of a factory. That's a better foundation than a lot of the breathless rare earth announcements you see from other countries that are essentially saying, "We found some stuff, send investment." The question is what it takes to get from here to an actual alternative to Chinese supply. And that question gets complicated very quickly. So how did China end up holding all the cards here? Because it didn't happen by accident, and it didn't happen overnight. This is one of those situations where, if you zoom out far enough, you can watch the whole thing unfold in slow motion and still somehow be surprised by where you end up. China currently controls somewhere in the range of 60 to 70% of global rare earth production. And that number, as eye-watering as it is, actually understates the real leverage because production is just the beginning. Processing and refining those elements into usable material, and then manufacturing them into the actual magnets that go into your wind turbine or your electric vehicle, that's where the concentration gets even more extreme. So even if a country manages to dig rare earths out of its own ground, it often still has to ship them to China to turn them into something functional. The mine is just step one of a very long chain, and China owns most of the rest of the chain too. Now, the standard shorthand explanation is that China got here through deliberate industrial policy, and that's true, but it's worth sitting with what that actually means in practice. Starting particularly from the 1980s and accelerating through the 90s, China made a strategic decision to build out this industry at scale. Invest in the processing infrastructure, tolerate environmental costs that other countries were increasingly unwilling to accept, and price the output in a way that made it essentially uneconomical for Western producers to compete. Deng Xiaoping reportedly said at one point that the Middle East has oil, but China has rare earths. Whether or not that quote is perfectly attributed, the sentiment captures the policy logic pretty accurately. And here's the part that deserves some honest acknowledgement, because it's easy to frame this entirely as China being aggressive, but the Western side of this story is mostly a story of choosing not to compete. The United States had a major rare earth industry. Mountain Pass in California was genuinely significant on a global scale for decades, and it was wound down, first scaled back, eventually closed entirely, largely because once Chinese supply came in cheaper, the economics stopped working and the environmental regulatory burden made the math even harder. Europe went through a similar, if quieter version of the same story. Investment dried up, processing infrastructure never really developed, and one by one, the reasons to bother domestically got outweighed by the convenience and cost of buying from China. So, what you end up with by the time you hit the 2020s is a situation where decades of rational, short-term economic decisions have produced a genuinely irrational, long-term strategic outcome. The West essentially outsourced a critical industrial input to a single geopolitical rival, and then expressed shock when that rival turned out to be willing to use it as leverage. The rare earth export Holt-Salberg references in the context of the recent trade war wasn't the first time China reached for this particular lever either. There was a significant episode around 2010 involving Japan that rattled supply chains and briefly caused a flurry of hand-wringing and investment announcements, most of which eventually fizzled when prices normalized and the urgency faded. That pattern, crisis, alarm, partial response, gradual forgetting, is pretty much the structural explanation for why we're still having this conversation in 2026. The environmental compliance angle is also real and shouldn't be glossed over. Rare earth separation is genuinely difficult and genuinely dirty, and doing it in ways that meet Swedish or broader European environmental standards costs more than doing it in places with weaker enforcement. That's not a knock on Chinese workers or Chinese engineers. It's just an honest accounting of where the cost differential comes from. Some of it is labor, some of it is energy pricing, some of it is that the externalities get handled differently, or sometimes not handled at all. When Salberg calls it a dirty business, he's not being dramatic, and the question of whether it can be made less dirty at competitive cost is genuinely unsettled, which is actually what makes the methodological core of this research interesting, because the Uppsala approach isn't just about finding Swedish rare earths and digging them up, it's about rethinking the process from the ground up in a way that might change the economics of doing it cleanly. The fridge analogy Salberg uses is a good one, and I want to spend a minute on why it actually matters, rather than just being a charming soundbite. The conventional approach to mining, not just rare earths, but most metals, is that you decide what you want, you go find a deposit that contains it, you extract it, and then you throw away or stockpile whatever else comes up along with it, because you don't have a use for it, and processing it further costs money. You're optimizing around a recipe that already exists and trying to make your raw material conform to that recipe. What Salberg's team is proposing to do is essentially the reverse. Instead of starting with a fixed magnet recipe and asking whether Swedish deposits can supply it, they're starting with Swedish deposits and asking what magnet recipes could be built around what's actually there. You take inventory of what's in the fridge, as he puts it, and then you figure out what you can cook with it. And while that sounds like it might produce worse magnets because you're working with whatever you've got rather than specifying exactly what you need, the counter-argument is that it could meaningfully reduce processing steps. Here's why that matters practically. A significant chunk of the environmental cost and the expense in rare earth processing comes from the separation stage, where you're trying to isolate individual elements from a complex mixture of many elements that all behave similarly in chemical terms and don't want to be separated. It's fiddly, it's energy intensive, and it typically involves solvents and acids that are not great things to have sloshing around in large quantities near groundwater. If you can design a magnet that uses a blend of elements closer to the blend that naturally comes out of the rock, you potentially skip or simplify some of those separation steps. You're not trying to force nature into your formula, you're building the formula around what nature gave you. Whether the magnets you end up with perform as well as the ones designed with more precise elemental specifications is a real question the research hasn't answered yet, and we'll come back to that. But the theoretical logic for why this approach could reduce both cost and environmental impact is coherent, not just wishful thinking. Now, the water and energy point Sahlberg makes in passing is worth flagging too, because it's easy to hear it as vaguely boosterish and miss that it's actually addressing a specific technical constraint. Rare earth processing, particularly the hydrometallurgical separation methods that dominate the industry, uses a lot of water. A lot. And Sweden has abundant freshwater resources and relatively clean hydroelectric power, which means two of the major input costs and environmental pressure points look better there than they would in many other candidate locations. That's not a guarantee of success, but it's a genuine structural advantage, not just national pride talking. The piece this still leaves wide open, and this is where we need to have an honest conversation, is the separation chemistry itself. Even with a more deposit-matched recipe, you still have to do some separation. And in rare earth deposits, you very commonly find thorium and uranium present as geochemical companions, radioactive elements that have to be managed carefully and that add regulatory complexity, waste handling costs, and public perception problems to any extraction operation, regardless of how thoughtfully you've designed your magnet formula. Sweden's strong regulatory environment is an asset in terms of making the process credible and transparent, but that same regulatory environment means you can't simply hand-wave the radioactive byproduct question. It has to be dealt with properly, and dealing with it properly costs money. So the honest version of this story is, the approach is smart, the structural inputs are genuinely favorable, the environmental costs are real and not fully solved, and whether the numbers ultimately work at commercial scale is a question this research project is not yet positioned to answer. That's not a criticism of the research. It's doing what basic research is supposed to do, which is build the scientific foundation that makes the harder economic and engineering questions answerable later. But it does mean we're somewhere in the early chapters of a story that has a lot of plot left to go. Let's be honest about where the skepticism lives, because there's a lot to be genuinely excited about here, and also a lot of distance between this is promising and this solves the problem. Start with the timeline. Sahlberg himself says, this interdisciplinary effort is expected to continue for many years. That's not hedging or false modesty. That's the actual shape of this kind of work. You're talking about cataloging deposits across an entire country, building new theoretical frameworks for magnet chemistry, testing those formulas at a materials science level, and then, if all of that works, handing the findings off to an entirely different set of actors who would need to permit, finance, build, and operate mines and processing facilities at commercial scale. Each of those handoffs is its own multi-year saga. So when we're talking about whether this research can move fast enough to matter geopolitically, the honest answer is probably not in the near term. China halted rare earth exports during the current trade war. That's happening now. This research is building a foundation that might matter in 15 or 20 years, which is genuinely valuable and genuinely not the same thing as a solution to today's supply shock. And then there's Europe's permitting problem, which anyone who has watched the continent try to develop its own critical mineral capacity over the last decade will find very familiar. The Nora deposit outside Grena has been kicking around as a prospective project for years. It has faced legal challenges and regulatory hurdles that have stretched the timeline dramatically. And that's a known, high-grade deposit, not a greenfield discovery. Sweden has better environmental credibility than a lot of its neighbors, which theoretically helps, but better and fast are not the same thing. European democracies have a real tension built into them. The same public values that make a cleaner supply chain politically appealing are the same values that generate sustained opposition to mines. That tension doesn't resolve itself just because the strategic logic is compelling. The application-inspired basic research framing is interesting too and worth sitting with. It's positioned as something more grounded than pure science, tethered to technological relevance, not just curiosity. Fine. But basic research is still basic research. It answers fundamental questions that then have to be translated by engineers, scaled by industry, and financed by someone who believes the economics will eventually work. Each of those steps has its own failure rate. The history of materials science is full of elegant laboratory results that never made it to market because the gap between a proof of concept and a manufacturable product was wider than anyone anticipated. None of this makes the research a bad idea. It's clearly a good idea. It's just not a silver bullet. And I want to be careful about the way these announcements can get received, as if the hard work is basically done and we just need to wait for the mines to open. Now zoom out, because what Sahlberg said in passing is actually the more revealing part of the story from a geopolitical standpoint. He named 3 things in one breath. China, halting rare earth exports during the trade war, Trump's Greenland move, and the US-Ukraine mineral resources agreement. He wasn't editorializing. He was giving examples of what the geopolitical landscape looks like right now. And what those 3 things have in common is that they are all, in different ways, powerful actors treating mineral access as a first-order strategic priority rather than an economic afterthought. The Greenland angle is almost too on the nose. The United States, the wealthiest country in the world, is making territorial maneuvers toward a Danish autonomous territory, partly because of what's in the ground there. That's not a metaphor for how serious this has gotten. That is how serious this has gotten. Similarly, the mineral resources agreement with Ukraine, struck while the country is still actively at war, is a signal that the calculus around critical supply chains has moved from something we should think about to something we are willing to build geopolitical architecture around right now. Sweden's research sits inside this wider scramble as one node among many. It's not leading the realignment. That realignment is already happening, regardless of whether any single university project succeeds or fails. What the Uppsala work represents is one bet in one country on a specific methodological approach to the supply problem. Europe is also looking at deposits in Scandinavia more broadly, at the Greenland situation as it unfolds, at recycling and urban mining as partial answers, at whether processing capacity can be built on the continent even if raw material extraction stays concentrated elsewhere. This is a multi-front problem, and Sweden is one front, which is actually what makes it worth paying attention to, even if the timeline is long. The global realignment around critical minerals is not going to wait for the science to catch up. It's going to push ahead on political deals, on investment flows, on trade agreements, with or without an elegant materials chemistry solution. What research like Sahlberg's could eventually do is give that realignment somewhere useful to land. A domestic supply base built on a smarter, cleaner foundation rather than just a rushed extraction scramble that recreates the environmental problems everyone is theoretically trying to move away from. So here's where I actually land on this. The methodology genuinely interests me. The idea of designing the recipe around what's actually in the fridge, rather than forcing a mismatch between deposit chemistry and manufacturing specs, that's not just clever framing for a press release, that's a real potential efficiency gain, and if it reduces the number of processing steps and the volume of toxic chemistry involved, that matters. The environmental piece is not window dressing. What I'm more uncertain about is the economic reality on the other end. Even if this works scientifically, even if the magnet recipes test well and the processing footprint is meaningfully lower, you are still asking Western consumers and Western manufacturers to pay what will almost certainly be a higher price for materials produced under a stricter regulatory regime. That premium is real. It existed before this research started, and it will exist after. Clean supply chains are more expensive to build and operate. Whether the market, or more likely, whether governments, through policy, will actually sustain that premium over time is genuinely an open question. We don't yet know which Swedish deposit grades out best under this full-spectrum inventory approach. We don't know what the actual magnet performance trade-offs will be when you optimize for available elemental ratios, rather than ideal theoretical compositions. Maybe there aren't meaningful trade-offs, maybe there are, and that's something the research will eventually have to show. And we don't know whether the public appetite for domestic extraction will hold in Sweden once an actual mine, with actual trucks and actual tailings, is the thing being proposed rather than a university research program. Those are the questions that don't have answers yet. And I think the honest thing to say is that Sahlberg's team is doing the right work at the right time. And we are still very much in the early chapters of a story whose ending depends on a lot of factors that a materials chemistry lab cannot control.